that one or the other of them would always be in the hospital to help us if we needed help, and that was true. Ray Adams came very early in the morning and was always there, and TMS was a similar type thing, I think. I wasn't the only person that was intellectually stimulated by the fact that you could see it actually. He showed me that when blind people read Braille, they do increase the activity of the sensory motor cortex more than you would expect. But the interesting finding was that, this is another example in our work where we were demonstrating this very interesting phenomenon and showing that this interesting phenomenon was actually functional.
Welcome to Stimulating Brains.
Hello and welcome back to Stimulating Brains. As many episodes, this episode is truly special. And I had the big honor to talk to Dr. Mark Hallett from the NIH. There are so many things to say about Mark, and I don't know where to begin, but I'll read a little bit about his short bio. So Dr. Hallett is an NIH distinguished investigator and the chief of the Human Motor Control section at the National Institute of Neurological Disorders and Stroke in Bethesda. He trained at Harvard Medical School, NIH Mass General Hospital and the Institute of Psychiatry in London. From 1976 to 1984, Dr. Hallett was the chief of the Clinical Neurophysiology Laboratory at the Brigham and Women's Hospital and rose to associate professor of neurology at Harvard Medical School. From 1984 on, he has been at the NIH, where he also served as clinical director of NINS until July 2000. He's past president of the International Federation of Clinical Neurophysiology and current president of the newly founded Functional Neurological Disorder Society. Dr. Hallett is also remote past president of the Movement Disorder Society and past editor-in-chief of Clinical Neurophysiology. He has won many awards, including, in October 2019, the World Federation of Neurology Medal for contributions to neuroscience. His work mainly deals with principles of motor control and the pathophysiology of movement disorders. Dr. Hallett has published an incredible 1,200 scientific papers with more than 160,000 citations and currently has an H-index of 212. And according to research.com, he's the 75th most cited researcher in the US and 104th in the world. Now, beyond this more formal introduction of Dr. Hallett, I think what makes him truly remarkable is also his legacy of mentorship. There are so many famous people that trained under Mark and rose to giants in the field of TMS and movement disorders. As you will hear, two of the most influential TMS researchers, such as Mark George and Alvaro Pasqualeone, have trained under Mark, and you can pinpoint their scientific beginnings to Mark. And as I'm German, I knew that two of the academic neurology chairs in Germany trained under Mark, but I learned after talking to him that it's actually 4 that trained with Mark. And that's 4 out of maybe 15, counting the bigger university hospitals in the country. Speak of legacy. In our conversation, we talk about the origins of TMS and how Mark potentially single-handedly put TMS on the map, together with maybe John Rothwell and some other folks that were investigating TMS early on. And we also then talk about his involvement in movement disorders, such as Parkinson's disease, dystonia, arthritosis, and more recently, functional neurological disorders. So I'm pretty sure you're gonna enjoy this conversation as much as I did. Thanks for tuning in, Stimulating Brains with Dr. Mark Hallett. So, Dr. Hallett, Mark, it's fantastic that you could join us. So thank you very much for your time. You just told me how busy you are right now, despite retirement, and so I really honor that, and it's fantastic that you could take the time. As you may know, I often start with the first question about hobbies, and I will have already introduced you more formally by now, so we can jump right in. So before we get into science, what do you do when not involved in work or science or so?
Right. So I do try to get a little bit of exercise. I do try to read for pleasure in the sort of small moments. I enjoy vacations, actually, and particularly vacations in warm places, and particularly in the winter. So,
Nice.
so my wife and I have usually in the last few years and now more recently done more time in warm places in the winter, like Hawaii and the Caribbean.
Great.
And I also like traveling to other places as well. Like traveling really all over the world. All the places are fun. And when I get there, one of my favorite hobbies is photography. So I like to take pictures of these different things that I find interesting.
Great.
And I suppose that I should also note that I really enjoy being with our family. This is one thing that my wife and I are particularly lucky. We get along very well with our children and grandchildren, and we enjoy visiting them and even also traveling with them.
Fantastic. What has been your favorite travel destination of all times?
That's always difficult. People ask me that often, and it's hard to say. I guess one of the ones that I really enjoyed a lot was a family trip that we took to the Galapagos Islands.
Wow.
And I must say that that was so good from so many points of view that it clearly makes it a very top-ranked vacation.
Yeah.
Yeah. We first of all went with the family, so it was a lot of very nice together time. But they are very interesting places to visit. You can see where Darwin was. You can get a view that he got of the different animals and the different types of locations. So there's history there. There's a lot of nice outdoor activities of various kinds with different animals, plants, geology.
Great.
So it really is a terrific vacation, and I guess when people ask me about vacations, I often do recommend that one.
Sounds good. And the photography, is any of that publicly visible? Any of your pictures, or is that all private?
Well, it's largely private. If you ever come and visit my office at the NIH, you'll find my pictures all over there. And
Great.
And actually, now that you asked that question, and I hadn't thought about this in a long time, but there was a period of time, maybe may have been about 15, 20 years ago, where for a couple of years, I think it was largely through the American Academy of Neurology and maybe in the American Association of Electrodiagnostic Medicine, they tried to raise money with auctions. And I'm not sure I don't think they're going on anymore, but there were these auctions, and I actually donated some of my photographs to those auctions.
Oh, wow.
And people actually bought them.
I'm sure. I would buy one. Yeah.
So there are some of them around. I don't think you'll find them in any museum, but you may find them occasionally in other people's offices or homes or something like that.
I'll follow up later. You don't have to answer now, but maybe we can. You want to send us one for the website for this podcast, so we can maybe exhibit one of your favorite pictures, if that could be an option. Anyways, moving on. Who were your key mentors and in your career, and then also turning points that led to your fantastic career?
Yes, well, thank you for that question. I have actually been thinking a lot about it in recent years for two reasons. One, I have retired recently, and I spent my retirement talking about my mentors. Also, about a year ago or so, I was asked by the uh, movement disorder group in the Commonwealth of Virginia to give a lecture on the last 50 years of my career and what was happening in neurology, and I thought about my mentors during that period as well. So there's really a very large number of them. As far as I'm concerned, I was very lucky in my mentors over the years. I had a lot of very important influences, and I think that certainly helped to move my career along. Let me just, I just mentioned a few of them in this regard. I suppose the most obvious one is David Marsden, who was, I guess, my last mentor. And I took a fellowship with him after I finished my neurology residency and before I took my first job. And I think, as everyone knows, he was a very important figure in the history of movement disorders, along with Shan, who I also got to know very well. They were really the founders of the modern field of movement disorders. And he was a very good thinker and inspired me in really very many ways, both in the physiology of movement and in understanding clinical movement disorders. So he was really an important person. My mentors during neurology residency, of course, are also important to anybody who is a neurologist, and I was lucky to be at the Massachusetts General Hospital in the last days of Raymond Adams and C. Miller Fisher, and it's hard to imagine a combination of neurology mentors better than they were.
Yeah.
They are, everyone knows them as very important founders of the field, again, with large emphasis on clinical neuropathological correlation. And I learned a lot from them. As Ray Adams told us at the beginning of our residency, that one or the other of them would always be in the hospital to help us if we needed help, and that was true. Ray Adams came very early in the morning and was always there, and C. Miller Fisher arrived a little bit later but stayed there very late at night. And so
wow. Okay.
If we ever needed them for anything, we could just give them a call and get some help from them, and very important guidance. There are many other people. I suppose just in terms of directing me to the field of movement disorders, another important person in that regard would have been Malin DeLong and Ed Everts. When I was a fellow at NIH, I was actually doing membrane biophysics, but there was a very nice weekly motor control meeting that Ed Everts organized. Malin was a fellow at that time. And we also had a seminar or a journal club for anybody who was interested in neuroscience, and Malin was part of that journal club, and Everts and Malin and perhaps some other people which I could mention if I went into more details, influenced me to get interested in the motor system. And then when I was in my residency and had an opportunity to start some research, I decided to work in the motor system. And it was because of that background influence that we had in the journal clubs. Even though I was working in membrane biophysics, I still was learning about the motor system.
Fantastic. I wouldn't even exactly know what membrane biophysics means. Is that? But it seems
right. Yes. So I was actually studying the biophysics of action potential production.
Okay. All right. Okay. So membranes of neurons. Okay.
Yes, and we were working with the squid giant axon.
Sure.
And, looking back on that time, it was very interesting because a lot of our observations then have been converted into other types of things. For example, we were using voltage-sensitive dyes in order to study the biophysics of the membrane. Well, that was helpful at the time, but of course membrane-sensitive dyes have now been used as markers of action of cells that have been used in multi-arrays to understand the way that neurons are functioning and interact with each other. We also identified that some of those dyes that were able to be polarized lined up in the direction of axons. And some of that information has been used as the basis of the biophysics of DTI and MRI.
Yeah, great.
So, a number of these very basic types of observations become useful. Then actually another observation that we made at that time, it had been speculated that, very strong speculation, of course, that calcium entered an axon during an action potential, but it had never been demonstrated.
Oh, wow, okay.
And so we were the first ones to demonstrate that.
Oh, wow. Did not know that.
So there were a lot of things that I did in those years doing membrane biophysics that I haven't gone back to, but they worked at the time.
Fantastic. So I have to ask, small jump, but since I am sitting in the Brigham and Women's Hospital in Boston, you from 76 to 84, you were the chief of the clinical neurophysiology laboratory here at the Brigham and Women's, and rose to associate professor at Harvard of neurology at Harvard Medical School. Before that, you graduated from Harvard with an MD and trained at the then so-called Peter Bent Brigham and, as you mentioned, Mass General hospitals. So can you summarize a bit what Boston meant to you and how your days were, even as a student and then going up to associate professor? You spent a long time here in the city. Any memories from Boston? I'm sure, but what are the salient ones?
Well, it's hard not to have memories. Cliff Saper once introduced me as Preparation H. Since I had gone to Harvard College and Harvard Medical School and did my clinical training at Harvard and then started on the Harvard faculty, I had been there for really much of my career. So that was Preparation H. So I certainly had when I got to medical school, of course, the Brigham was one of the important hospitals, and I was in and out of the Brigham all through medical school. And then I was happy to do my internship there. At the time, H. Richard Tyler was the head of neurology there. And then fast forward a number of years to when I was looking for my first job, and Tyler had an opening, and I was very pleased to accept the opportunity to come back and work there. My job was to run the clinical neurophysiology operation, which I did pretty much on my own. At that time, it's hard to believe, given the size of neurology departments now, but neurology at that time was just a subsection of medicine. It wasn't a department.
Oh, wow, okay.
And we just had 4 neurologists.
4?
4, that was it.
But, okay, 4 plus residents, I assume.
Right, well, we also had residents, correct.
Yeah.
But there were just 4 of us faculty, and so the neurophysiology lab was entirely my area, and so I spent at least, I guess, probably 60-70% of my time doing clinical neurophysiology, 30% doing clinical, and another 50% in my spare time doing research.
Makes sense. Okay. Yeah. I can imagine. Yeah. Wow, that's really little for a big hospital like the Brigham. It's hard to imagine now. You're totally right. Interesting. And so can I ask, where did you live in Boston? What do you like in private life? What do you miss of Boston, maybe?
Right. So, I guess most relevant is when I was in medical school, and I had actually married after my first year in medical school. My wife and I lived in Brookline. During my residency, we lived at Charles River Park, which everybody knows there are the apartment buildings next to the Massachusetts General Hospital. And then when I came back on the staff, we lived back in Brookline again. Brookline was advantageous. I could walk to work, and I really enjoyed that part of it. I have, of course, a huge number of memories about Boston after having been there for 20 years altogether. But I wasn't that unhappy to leave. I had also spent 2 years in Washington as a fellowship between internship and residency. That was during the Vietnam War, and that's another whole story about how people were moved around during the Vietnam War, but it worked out well for me, having been at the NIH as a fellow during that time. But I enjoyed Washington, so I was pleased to go back to the NIH after having been at the Brigham for about 8 years or so, and happy enough that I spent the rest of my career there.
Yeah, of course. I live in Brooklyn, by the way, had to say it. And I think Mike Fox just became the Raymond Adams Chair of Neurology now. And of course, Miller Fisher rings a bell. And so it's fantastic to see, many big names at the time in Boston. And so, I can also walk to work. So I can relate to that. It's fantastic. So I think from 1984... when I was born, you were at the National Institute of Neurological Disorders and Stroke, so the NINDS, or NINDS, where you also served as clinical director of NINDS until July 2000. What were your roles at NIH? And can I also ask, did you continue to see clinical patients there at that time?
Sure. So, first of all, it is interesting that names changed a lot from time to time. When I went down there, it actually wasn't NINDS, it was NINCDS. It was the National Institute of Neurological and Communicative Disorders and Stroke. And at some point, I've forgotten exactly when it was, communicative disorders split off because the otolaryngologists wanted their own institute. So then it became NINDS at that time. So when I went down there, I had two jobs. One was my research position, which was the head, which I set up my own section called the Human Motor Control section. And the second one was clinical director. As you pointed out, that only lasted 17 years.
Long time.
That was an administrative position in which I had responsibility for running the clinical program and dealing with all of the clinical issues, the nursing staff, clinical facilities, clinical neurological consults to the rest of the NIH hospital, and so on. And then in my research side, I set up a group interested in motor physiology. But as with most of the groups on the clinical side of the intramural program, we also did clinical training of fellows. So I always had clinical neurologists who were training as well as doing research. So we had an active clinical program from the very beginning, and that I continued even when I stopped being clinical.
Okay.
But just to give you one anecdote from my job as being clinical director. There are many, of course, but I'll just give you one fun one. I guess it wasn't that much fun, but there's one interesting anecdote. So, as I mentioned, it was NINCDS, and therefore the Institute was responsible for neurology, neurosurgery, and otolaryngology.
Oh, okay.
That was our responsibility. Now, NINDS has always had neurologists and neurosurgeons, but when I arrived there, we had no otolaryngologists, even though we were responsible for otolaryngology. So one Sunday night, I got a telephone call late on Sunday night from the NIH, from one of the doctors there, who said that they had a patient who had a severe posterior nosebleed, and would I help them with that problem?
Yeah.
Now, physicians will immediately identify the fact that posterior nosebleeds are extremely important because people can easily bleed out, and they're very hard to control, which is why I got that call. But as the clinical director, I was responsible, but we had no otolaryngologists. So that's what I told the person who called. I said, well, I understand that I'm responsible, and this is an important problem, but I can't really help. I don't know how to deal with a posterior nosebleed myself. Why don't you just call the general surgeons and see if they can help you? And the guy said, well, I am the general surgeon.
Okay.
So I said, well, just do your best, and I hung up. So I told Joe Martin that story. Joe at that time was the chair of neurology at the Mass General, and he said, well, at least you had a good department of transfusion medicine at the NIH.
Yeah.
Interesting. So that gives you an idea about my clinical responsibilities that I have.
Yeah, very interesting. So because I'm live in the US now, but I'm just 2 years in. So for many like me, the NIH is a funding agency, but of course there's also a lot of research going on on site, and also there's clinical service. So it's very interesting to hear a bit how the intramural science works, and then also, is it a regular hospital or is it more a research hospital? Do people come there from the Washington and Bethesda area to seek help, like medically? Is it a normal hospital? Can you talk a bit about that, and maybe the same for research? Funding is different.
That is an important question, and many people don't understand it. It is a 100% research hospital.
Okay.
Patients can come there only by invitation.
Makes sense.
And every patient is on a research protocol. And the hospital doesn't necessarily have all specialists, as you just heard.
Yes.
So in subsequent years, I think things improved, and we made sure that we had adequate coverage in all areas. But at the time I got there, we did have a failure in otolaryngology. But if you're running a hospital, you do need expertise in all the different areas, and there are, so given that is the case, the nature of the patients in the hospital are highly varied. Some are in the hospital just because it's convenient to do the research. Mm-hmm. And some of them are in the hospital because they are very sick. Okay. So there's a mixture of cases, but whatever, they're all on research, and it is probably the largest research hospital in the world.
Yeah, I can imagine. Yeah,
because of that. Yeah, it's a very large operation, and it's 100% research.
Got it. Interesting. And then research as an NIH researcher, I think one difference is it's typically hard funding. Is that correct, or do you guys also apply to NIH grants within the system?
So, yes, we do have sort of very good baseline funding. And one of the sources, but we can supplement it with other grants, but the grants cannot come from NIH.
Makes sense. Okay.
So that we can't mix intramural money and extramural money.
Got it.
We could get a grant from a patient foundation or from some other group, but couldn't get a grant from extramural NIH.
Okay. Thanks so much for this more basic walkthrough. But let's focus more on your personal research. You're famous for many things, I know, but for me, I think two main big factors stick out. One is that while you may not have invented TMS, transcranial magnetic stimulation, you have essentially put it on the map, I think, single-handedly with your team and your mentees and so on. And the other could be that you're a one-of-a-kind expert in movement disorders, and maybe, if I interpret correctly, mainly for dystonia, but I'm sure also other rare movement disorders. So your research has always focused on principles of motor control and the pathophysiology of movement disorders, and I think TMS has been a tool for you to investigate that. Is that a good summary of the big picture? Or?
Yes, I would say that's right. My interest has always been in fundamental principles of movement, both how we make movement and how we learn movement, and then how that falls apart in different types of disorders. And in terms of the disorders, that has varied over the years. In fact, when I first went to NIH in 1984, the field of movement disorders really wasn't very well developed yet. It was just sort of beginning. And my interest really was in motor control. And so I called my research unit the Human Motor Control Section. If I had founded it maybe 5 years later, it probably would have been the movement disorder section.
Got it. Yeah.
But at that time it was motor control, and actually our main project started out was in stroke recovery.
Got it.
Because I thought that was a very interesting issue in motor control, how people recovered from stroke.
Yeah.
But I also was interested in Parkinson's disease, ataxia, many different things, and I suppose the earliest work that we did there, in addition to stroke, was on ataxia and Parkinson's disease. And then diseases have varied over the years that I've focused on. So for a long time, as I say, we did ataxia, and then that sort of faded off. We got interested in essential tremor, and that went to some extent, Tourette's syndrome. Parkinson's disease has always been in the background. There's been sort of a steady level of Parkinson's disease research. And then we got interested in dystonia, I suppose because of the botulinum toxin business. When botulinum toxin came along, we got interested in that, and that sort of spurred my interest in that field, which is true, was a clear area of emphasis for many years. And then in the last 15, 20 years, I've moved my main emphasis to functional neurological.
Yeah.
So I've been through the whole gambit of different movement disorders over the years, but the general principles of motor control, of course, are similar. So that's been sort of the basic foundation. And actually, I'd like to say that the different movement disorders help us get different insights into the normal principles. So that if your basic interest, as is mine is in motor control and how the brain works to make movement, then the more types of lesions you have, or the more types of pathology you have, the better insights you can get into the way that things work or don't work. And of course, as a clinical neurologist, when we got interested in the disease, we also got interested in its therapy and all the different other aspects of that. So these things tended to sort of spread out. Now, in relation to TMS, I would say that it was just, in a sense, one of the tools that came along that I thought could be useful in our studies. Now, that you could say that also is true of PET and MRI and all these different tools. As they came along and we thought that they could be useful, we began to employ them in our work. So yes, when TMS came along, we started using it, but the early studies had to be basic studies because people didn't know quite how to use it.
Sure.
Actually, if you look at my publications, that's also true to some of the studies we did in PET, some of the studies we did in MRI. In fact, I was just talking to somebody about this the other day. We had been doing all of our functional studies with neuroimaging using blood flow PET. And then functional MRI came along.
Yeah.
Well, we did a number of studies trying to see the relationship between blood flow PET and fMRI.
Makes sense,
So,
sure.
Just sort of basic studies trying to understand there's sort of general principles about how you could use it. And that was, in a way, similar with TMS. So, in a way, you could say I have always liked to use different fun tools as they come along.
Yeah.
And TMS was not necessarily unique. It was one of the ones that I certainly thought was going to be useful. And as soon as it came along, we actually used it. And in fact, it goes back, in terms of brain stimulation, it goes back one step further than TMS, and that was because of the high-intensity transcranial electrical stimulation. That's where we actually began.
Okay.
And in terms of the history there, you and your listeners may well remember that it was this paper by Merton and Morton that first demonstrated that you could stimulate the motor cortex through the intact scalp, and that was with a high-intensity electrical stimulation.
Got it.
Now, there's an interesting story about that, actually, which I think is worth knowing, and that is that Merton was actually studying muscle at the time, and he wanted Morton, who was a very good engineer, to create a stimulator that would activate muscle fibers directly, as opposed to stimulating the intramuscular nerves, which you can stimulate at a lower threshold. So he wanted a high-intensity stimulator. So Morton built it for him, and then Merton tried it on the muscle. It worked just as he wanted. And then he said, gee, maybe it'll be strong enough to activate the brain. So he put it on his head, and it worked. And he published that in Nature. So
I was not aware of that. Wow. Okay.
So that excited everybody interested in brain physiology, and that began to be used for various things. And John Rothwell particularly picked up the method. Merton and Morton and Marsden had worked together, and so there was a very close collaboration there. And John Rothwell was working as the principal physiologist in Marsden's lab at the time. He picked that technique up and began to use it, and I was very jealous. I wanted to do that too. And this is an interesting story. John was coming over to visit us at NIH at one point, and I asked him to bring over a stimulator.
Great.
Now, of course, it was not FDA approved, and taking one of these stimulators across the ocean wasn't necessarily a good idea, and had there been all the heightened security of various kinds, he might not have made it. But in any event, he actually brought the stimulator over, and we tried it in the lab on ourselves, and I thought it was a great tool. So we actually kept it. And then we ordered it from the company subsequently, and the company sent us an empty box because we already had it.
And sorry, that was electrical or magnetic already?
Yes.
Okay.
Yes.
Oh.
It was a high intensity electrical. And
since that is not used anymore, at least I'm not aware,
yes,
is
right,
that pain?
right. So,
is that painful, or is that?
Yes, it was very painful.
Okay.
It was very painful. And fortunately, within a very short period of time, Barker first was able to work out the engineering to do transcranial magnetic, and that rapidly took over. But again, just for a number of years, it was of interest to compare electrical and magnetic. They don't actually stimulate the brain exactly the same way.
Sure.
And it was very interesting to figure out why they stimulated the brain in a different way, and could you learn things from electric that you couldn't learn from magnetic, and vice versa. Yeah. So there was a lot of work that went on in that regard, but the studies with the transcranial electric were always much harder to do because it was very painful.
I'm sure.
But I suppose there's not very much going on with high-intensity transcranial electric anymore, but of course, low-intensity electric is,
of course,
really very popular now.
TDCS, so, yeah, sure.
Yeah,
sure.
So I think the high-intensity has been switched to low-intensity, but I would say that there are still potential experiments where transcranial electric could be advantageous, but it's hard to get cooperation from patients in that regard.
And to get the story right, so you trained with Marsden, that was in England, right?
Correct.
And Rothwell was also in England, and but when you started with TMS, you were already at the NIH, so it was a collaboration, or you visited, or?
Right.
Okay.
Right. Long time later. So Marsden's lab, when I came there in 1975 for a year. There was a PhD student in the lab along with me, and the PhD students were PhD students that were sent to David Marsden from Pat Merton in Cambridge. And the student there was Jane Adam, and she was finishing her PhD. So she finished her PhD in July 76 when I finished my fellowship, and we both left. And Pat Merton sent John Rothwell to Marsden's lab as the next PhD student after Jane Adam. So John came to the lab in replacement of Jane Adam, and I was also leaving at that time. So we didn't really overlap at that point. But then it was many years later that was the beginning of TES and TMS.
Got it. Okay, super. So can we talk about TMS a bit? So how did you first come into contact with it? Were you visiting in London or in the UK, or was it communications you had, or how did you see it and then say we have to play with that?
So I guess I first saw it demonstrated at a meeting of the International Federation of Clinical Neurophysiology. The International Federation of Clinical Neurophysiology was always had very good meetings. They were held really every other year, but they had slightly different names. I won't go into all that at that time. And they often had demonstrations of new technologies. And actually, many of those demonstrations were very important demonstrations, and one of them was at least the first time I saw transcranial magnetic stimulation demonstrated. And as I mentioned, we already were using TES.
Sure.
And we'd heard about TMS being much less painful. And when I saw TMS, I said, gee, we really need that rather than using TES. But again, while we're just talking about anecdotes of various kinds and the sort of importance of the International Federation of Clinical Neurophysiology demonstrations, another one that comes to my mind was a very important demonstration of the value of single fiber EMG. There were various techniques to identify myasthenia gravis that had been suggested. Repetitive stimulation was the sort of standard, and it still is used much of the time. John Desmet had come up with a very complicated method to use repetitive stimulation to make it more sensitive. And Eric Stahlberg had invented single fiber EMG and was using that to identify patients with myasthenia in a sensitive fashion. And at one of these demonstrations, there was a comparison of the Desmet technique and the Stahlberg technique on a patient who had possibility of subtle myasthenia. John Desmet spent a half an hour studying his patient and failed to show any abnormality. Eric put his single fiber needle in and in about 10 seconds had identified a motor unit pair with increased jitter, indicative of myasthenia. Well, that convinced me and many other people that there was value in single fiber EMG.
Sure.
And I think that was an important demonstration. And TMS was a similar type thing, I think. I wasn't the only person that was intellectually stimulated by the fact that you could see it actually demonstrated in person at that meeting.
And at the time, could you then just, was there a company already? Could you just buy a device, or was it always custom?
No, that was much more difficult. It was difficult to get them. They were being made in England, but it was hard to get a hold of one. Then there was a U.S. company that came along, and that was the Cadwell company. And the Cadwell company had really a very good machine for doing TMS, and actually they had a variation that could do repetitive TMS. We got a Cadwell machine first, and then Alvaro Pasqualeone came as a fellow, and he had been using repetitive TMS during his neurology residency in Minnesota. And he had a relationship with the Cadwell company, and with his relationship and our relationship with Cadwell, we got one of the first, or probably the second or third, repetitive TMS devices from Cadwell. And then we began using it in a very intensive way. And in the beginning, going back to things we were talking about before, while our intention was to use it for studies of motor control, in the beginning we just had to see what it did.
Sure, of course. Yeah.
So a lot of our studies in the beginning were just very basic studies, trying to understand what TMS did, how it activated the brain, what was the effect of repetitive stimulation. And one of the things, of course, that was a significant issue, and I suppose this is worth at least a couple minutes of discussion, is safety.
Sure.
Safety of TMS. Now, we didn't really have any idea of what was safe with repetitive TMS and what wasn't. And but the IRB allowed us to, move ahead cautiously with different things. And at one point, we had a seizure in a normal volunteer. And that was very, very frightening to us, of course, as well as the volunteer. And the IRB wasn't happy with that either, and they shut us down for a very short period of time. We told them, "Oh, this appears to be rare, and we'll keep our eye on the situation." And we gave them parameters which we'd use, and so on. They said, "All right, you could go back into business again." We went back into business, and then within a short time, we had another normal volunteer with a seizure.
Yeah.
Well, they shut us down completely again, and they showed no signs of wanting to reopen all these investigations that we were doing. So I got into negotiation with them, and I said, "Well, look, let's organize," because people around the world were beginning to use it. We weren't the only people at this point doing it. I said, "Well, look, let's get together a international group of people to discuss the safety of TMS, and in particular our TMS, and see if we can come up with standards that will be safe, and then we can come back to you and maybe we can go back in operation." So the IRB agreed to that, and then we set up a safety study, a safety meeting that we held in Bethesda, Maryland, and that went on for several days. And one of the issues, the biggest issue of concern, there were a lot of issues of concern, but the biggest issue of concern was seizures. And not only seizures, but the possibility of kindling. That is, if you create a seizure in a normal individual, could that seizure then lead to a later event of a seizure developing either there or at that spot or somewhere else in the brain? So we had probably a full day was devoted to epileptogenicity and kindling and things of that sort.
Yeah.
Very interesting types of studies. Everyone, people didn't know that much about TMS.
Of course, it's very important. It's early days. Makes sense. Sure.
And so we finally came up with a consensus. We built a table of what we thought would probably be safe intensities. We built that up on the basis of our own experience at NIH, studies that Alvaro had done, studies that Robert Chen had done, Leo Cohen, Eric Wasserman. A lot of people had been involved with studies that we had at that time, and we pulled all that together, what appeared to be safe, and then what appeared to be problematic, particularly our two seizures. And we developed a safety table that was published. Eric Wasserman took the lead in publishing that first safety paper. We brought the information to the IRB, and they let us go ahead with studies again.
Great.
However, within a short period of time, we had another seizure.
Oh no!
And
for you.
So what it turned out is that we had identified TMS intensity, TMS frequency, and the length of a train of our TMS as being relevant. Mm-hmm. What we hadn't identified as being potentially relevant was an interval between trains.
Okay.
And one of our investigators at that time, specifically Jordan Grafman, had done a study in which the intervals were very short. And that's what did it. A very short interval between trains. So it was a parameter that we hadn't identified as being potentially relevant. So that led to another paper in which we wrote dealing with the issue of interval between trains.
Yeah.
As being a fourth parameter of RTMS that would be relevant. In back to the IRB. The IRB finally agreed. They allowed us to go back to work again.
Okay.
And from that point forward, we've had no more seizures in normal volunteers. That safety table that we developed now the order of 30 years ago has been reconfirmed at the second safety meeting that we organized and the third safety meeting that we organized in roughly 10-year intervals.
Yeah.
So that has been the guidance for safe delivery of our TMS ever since.
Yeah.
So it's the whole story is an interesting story how this all.
Yeah. I may have been in Alvaro Center under Mike Fox when the third one came out, so I loosely remember that. It must have been around 2016-ish or so. And I think these are very highly cited papers and very important papers that you coordinated there. So that's fantastic. We have talked about your mentors in the beginning, but I think what you are very famous for as well is a legacy of mentees that really became very famous. And you mentioned a few of them already, really big names. Alvaro Pascual-Leone is one, then Mark George, I think, had a different supervisor but did TMS in your lab as well. In fact, I asked a few people for guest questions, and Mark George replied and has a guest question for you. And he asks, do you regret letting psychiatrists, particularly Dr. George, do TMS in the NIH labs in the early days?
Well, I mean, it's the exact opposite, of course, and Mark knows that very well. I have always liked collaboration, so that has been something that I've done all of my career. I remember, so at the time, we had the only TMS lab, of course, at NIH. They weren't that common anyway around. But Mark had the excellent idea that maybe you could treat depression using our TMS. He had been doing studies in neuroimaging using PET and had identified that there was hypometabolism of the left dorsolateral prefrontal cortex in patients who were depressed, and came to me with the idea that if we could indeed change the excitability of the brain using this new technique, whether if we directed it to that hypometabolism, we could increase the metabolism and we could help depression. Well, gee, that sounded like a good hypothesis to me, and I said, sure, let's go ahead. Go ahead, you're welcome to use it as you wish. And Eric Wasserman particularly got interested in helping Mark with those studies, and they proved to be one of the most successful things that we did. So I certainly don't regret getting involved with psychiatrists in this regard. I have always enjoyed my interaction with psychiatrists, and actually with my current interest now in functional neurological disorders, I'm still very much involved with psychiatrists at all levels.
Great. Other famous mentees include two of the neurology chairs in Germany, university hospital chairs. I think we only have around 36 hospitals, and larger ones maybe only 15, and two of the bosses of university hospitals are your trainees. Joseph Claßen is one in Leipzig and Christian Gerloff in Hamburg. And there's a guest question by Joseph Claßen as well that I'm going to play to you. It's an audio file, so let's try that.
Hi Mark, this is Joseph. It's good to talk to you, even if only via an audio file. It's been a long time since I spent my days in your lab, and I remember it was a great time. It seems funny though, that time is considered part of the early days, because even then I felt that the TMS field had matured quite a bit by the mid-90s. So here's my question for you. What was your primary driver to get into TMS research? As a tool to study physiology, or as a technique that promised to open up new therapeutic venues? And has TMS delivered on that promise? Take care.
Very good. Well, yes, I thank Joseph for that question, and perhaps just make one more point. There's one more professor that spent time in my group, and that's Old Zeeman.
I did not know that. So he's also chair. So you have three of 15. Fantastic. Wow, that's I wasn't aware. Sorry. Yeah.
And I guess if you want to go further in that regard, Gunter Deutschel spent a year sabbatical with us. He wasn't a fellow, but he was with us also. So
he's of course okay, yeah.
So
fantastic.
Actually 4 of the professors had spent time in our group. Well, I think that my interest really was of the choice of diagnostic or therapeutic. My interest certainly was in diagnostic in the beginning, but not necessarily diagnostic. It was really a physiological tool. Again, my interest was in motor control and the use in pathological situations was sort of secondary. But that was really the principal interest. But we quickly got interested in therapy after Mark George had shown that it was useful in depression. Then the issue came up, well, gee, maybe it can be useful in other situations as well. But there isn't any doubt that my first interest related to questions of brain physiology, the motor system particularly, and how it might be problematic in different pathological conditions.
After depression, what do you think? What would be the second next lowest hanging fruit for treatment? Which disorder?
Yes, well, that's a good question. I've generally thought that Parkinson's disease would be something that could be useful, at least in some regard. It always has seemed to be a low-hanging fruit in some way, but we haven't quite gotten there yet. But maybe it will be useful for some aspect of Parkinson's disease along the way. At the moment, we are doing a therapeutic study in functional neurological disorders at the NIH. And when I say we, it's really Dr. Sophie Cho, because I'm now retired so I can't actually be involved myself according to NIH rules. But we had published a pilot study of this, and then Sophie Cho has taken it now to a double-blind study. So one of the observations that we've made in functional neurological disorders is that there appears to be an overexcitability of the amygdala. And for that reason, then we would like to be able to dampen that hyperexcitability. Now, TMS as a tool can't quite get to the amygdala very well, correctly. So we are using a method that was developed for stimulation of the hippocampus, and that is to choose a spot on the cortical surface that connects to the amygdala and then try to influence the amygdala indirectly.
Yeah.
So we have done a study using fMRI, a spot in the dorsolateral, the left dorsolateral prefrontal cortex that is directly connected to the amygdala, and we're trying to influence the amygdala that way and hopefully dampen down the amygdala and improve functional disorders. We did publish a pilot study of 5 patients. That study was led by Vera Spagnolo, who is one of your colleagues at the Brigham, if you don't know her.
I don't, I'm sorry, yeah, okay.
Now, she is in the psychiatry department. She is one of the psychiatrists there, but she was the leader of that study, leader of that pilot study, and now we are, or should I say Sophie is conducting a double-blind study. So that one I have high hopes for. Just like in Mark George's study, it has a very strong, I think, pathophysiological rationale.
Yeah.
And should we be able actually to dampen down the amygdala, I think it has a good chance of being useful. So, in any event, low-hanging fruit, I don't know, but in any event, that's the fruit I'm going for at the moment.
Great. All right, I have two additional guest questions that would fit in here. They are by your academic grandson, so Joe Taylor, who trained with Mark George and is now a dear colleague here, also in the psychiatry department at the Brigham. First, he asks, please tell us one of your favorite aha moments from the early days of TMS. Was there a particular day or experimental result that stands out in your memory as one that convinced you that the field had substance or potential?
Right. So I guess the one that comes to me is this. It did have an aha part of it, but it was a little. But let me describe it. So one of the most interesting things that we identified during my career at NIH was transmodal plasticity. We had been studying the way that blind people read Braille. And these were studies that Alvaro Pasqualeone first developed, because when blind people read Braille, they read a lot of it, they use their hand a lot. So the question was, what happens in the motor system if you use your hand a lot? So we were doing studies of motor plasticity and hand use and so on that Alvaro had led, and that they were highly productive studies. And then a fellow came in the imaging area, Norihiro Sadato. He was a neuroimager and wanted to do some studies. I said, well, why don't you study this particular technique? Rather than using TMS, let's use, at that time it was blood flow PET, because this was earlier than our functional MRI, although we were just in sort of transition at that time. So he did, and the incredible aha is when he came, when Sadato came running into my lab and said, look what I found. And he showed me that when blind people read Braille, they do increase the activity of the sensory motor cortex more than you would expect if they do that. But the interesting finding was they also activated the visual cortex.
Oh, okay.
And that was an incredible observation that since vision wasn't going to the occipital cortex, now somatosensory information was. So then we wanted to know, so we had a correlation, but we didn't know that it was actually functional.
Yeah.
And Leo Cohen had been in the group. He went away for 4 years to do his clinical training in the United States, and he just was coming back to the lab at that time. And I said, why don't you take this on as a project, use TMS to interfere with the visual cortex as people are reading Braille, and see if you can show that the function of reading is not as good because you're interfering with the visual cortex. You're not interfering with the sensory cortex, but you're interfering with the visual cortex.
Yeah.
And Leo did that experiment, and it worked.
Wow.
We were able to show that you could interfere with the ability of blind people to read Braille if you interfered in the visual cortex. Now that was a extremely valuable experiment in showing that that this part of cortex was actually functional in this regard. And I think that that to me was a very important observation. And other people had showed that this type of stuff worked for that reason. But this is another example in our work where we were demonstrating this very interesting phenomenon and showing that this interesting phenomenon was actually functional.
Yeah,
That it actually
it's
worked.
beautiful. Yeah.
No,
Beautiful.
yeah. So these turned out to be back-to-back papers in Nature, and I think that these were two of my favorite papers, and
I'm sure.
it is sort of an aha in a way.
Yeah, no,
Altogether,
absolutely.
the whole thing is an aha story.
Very nice. His second question, also Joe Taylor, it would be great to learn about the scientific culture of the early days. How did groups with differing viewpoints or priorities navigate each other? How should newly trained brain stimulators build a sense of community that supports differing perspectives without creating fractions or factions?
Oh yeah, that is a good question. I guess in the early days, maybe because there was so much low-hanging fruit, to use your phrase from before, that there was plenty of work to be done, and you could work on a whole variety of areas, and you wouldn't be interfering with other people, and there were new things to learn, and everybody was excited by the findings that everybody else was making, and there was a lot of collaboration that was going on at that time. We were, in our group, always in discussion with John Rothwell's group in London. We were in a lot of active collaboration with Roger Krakau's group in New York City. At that time, we actually published some things together with them. So I think that it was easy, everybody knew everybody else, and people were very friendly and cooperative. And I suppose, again, it might have been the International Federation of Clinical Neurophysiology that was having meetings, getting international people together on topics like that was important. At least in the United States, one of the things that was interesting in terms of clinical neurophysiology developed in the United States as a EMG specialist group and an EEG specialist group. Mm-hmm. And when TMS came along, neither group was that excited about it.
Okay.
But the International Federation, where there were a large number of Europeans, where clinical neurophysiology was a unified field, TMS came along, it was more strongly embraced. And TMS was a very popular subject in the international meetings, so we all got together in these international things much more than any national meeting. So I think that was helpful too in getting people together to collaborate. I suppose these days things tend to be and also I guess it was easier to get academic jobs then.
Okay.
There wasn't as much competition as there is now in that regard. Academic positions, I think, were probably easier to get. There weren't that many neurologists. As I mentioned, we only had 4 at the Brigham when I started. So I think now things are a bit more competitive in many ways. But I think that the more that people can collaborate on stuff, the better. In terms of getting things done. I think that this is now being demonstrated in the genetics area a lot. There had been a lot of, when that started, there was an enormous competition. I guess there still is to some extent, But a lot of the progress in genetics has come from collaboration, people putting stuff together, getting larger numbers, and being able to get more useful data. And I think that that's very helpful. How to get people collaborating more, I guess, is having international meetings, having people go and hopefully interacting in a favorable way.
Yeah.
Helping each other move along in this.
Makes sense.
Yeah.
Great. So I'm sure the early days were full of anecdotes, and we've heard a few. Do you have maybe some more technical anecdotes of how the coils maybe malfunctioned, or how clunky they were, just to paint a picture of now we buy a device and it works. It's been approved and everything, but at the time, I'm sure things were more complicated.
Yeah, there was a lot of complicated stuff. I'll tell you one of the funny things that happened. So in the early days, we were trying to figure out how these different coils stimulated the brain. And it was, we were having a little bit of trouble figuring that out, where we needed help from physicists to tell us about what magnetic fields looked like and how they were likely to stimulate the brain and whatnot. And there were a number of coils that came out with different shapes and different sorts of designs. And in order to understand them, we wanted to know what the windings in the coil were like. How were the coils made? Well, none of the companies would tell us.
Mm-hmm.
They all were keeping it a trade secret.
IP, okay.
As to what they were. They didn't want to describe what the situation was. But we were working with a physicist who said, "Oh, that's no problem. We'll just X-ray them."
Aha.
So we X-rayed all the coils, and we could see the windings very well on all the coils. And then once they saw the windings, they could then calculate the electric field based on the windings. And so we wound up publishing a paper, which I think with a relatively famous illustration of a side-by-side X-rays of the coils and their calculated electric fields.
Great. So you published the trade secrets in a way.
So we published all that. That's one of the stories. There's another one that just comes to mind at the moment, and that is that we weren't exactly sure of the direction. Another thing we weren't sure of: what was the direction of the current flow in the coil? Was it going left? Was it going clockwise or going counterclockwise? Which direction it was going? And at some point, the companies put a dot on it or something to tell us which way was which. But apparently, for the coil that John Rothwell was using, the company had mislabeled it.
Huh.
And at one point, John realized that what he was saying was the current direction was actually the opposite. Mm-hmm. So he wound up having to publish a paper saying, those last 5 papers that we published, the coil current was actually in the other direction.
Interesting. It's not my fault. Yeah. Okay.
Not our fault. The current was going in the other direction for what we were told. So there was a lot of interesting stuff going on when we didn't really know, completely about all the stuff that was happening.
Yeah, no, absolutely. So the field of TMS has since exploded. Since, I say it again, you put it on the map. I really think that's accurate. Speaking of huge impact, maybe there could also have been some doubtful moments where you think, oh, is this going into the right direction? And here's a guest question now from an academic great-grandson, Shan Siddiqi, who trained with Mike Fox, who trained with Alvaro Pasqualeone on the topic. So Shan asks, sometimes when I do something stupid, my father feels personal responsibility, even when it's obviously not his fault. As arguably the father of the entire TMS field, do you sometimes get that feeling when people misuse it? Particularly when the misuse appears to be motivated by personal profit? Or has the baby grown old enough such that you can let it free?
Well, I guess first of all, I would argue with the premise there that I'm the father of the field. I would deny that. I think that there are a number of people who were more fathering than I was, or at least at the same sort of general level. John Rothwell certainly was at a or has been an extremely important person in this area, and then a number of other people as well. So I don't want your listeners to think that I accept the notion that I'm the father of the field.
But to the listeners, he still is the father of TMS.
One of the people in that regard.
Well, yeah, sure.
So I never really had a doubtful moment about the utility of the device. Both for diagnosis and treatment. I mean, we certainly had some downtime when we were concerned about safety.
Sure.
That I talked about, but I don't think I ever had a moment where I thought, "Gee, this is a device that's going to not be useful in the long run." Yeah. I thought the utility was going to be getting more and more, and I was happy to see it spread around in different ways. Interestingly, just as a comparison, I've been in this field long enough that one of the developments that was early in my clinical neurophysiology career was the use of evoked potentials, particularly for the diagnosis of multiple sclerosis.
Yeah.
Now, that was an extremely hot topic. People were doing all sorts of evoked potentials for the diagnosis of multiple sclerosis, and I was doing that too as a clinical neurophysiologist. But I must say that from relatively early on, I thought it was going to be a technology that would be bypassed. I thought that for the purposes of at least diagnosing multiple sclerosis, that it was not going to be the final answer.
Yeah.
That we would be doing it in a different way. And I think that turned out to be true. People still use evoked potentials. They're useful for certain things. But the main use by far was in making the diagnosis of multiple sclerosis. And I was generally doubtful about that. Not from the beginning. In the beginning, it was very exciting, of course, when you have a new technology. It is very exciting, but as we moved along, I got the sense that we would be able to do better with other approaches to that question, other than evoked potentials. And I think that turned out to be right.
A few more guest questions. One is from Mike Fox, and I think we partly covered it, but we can rephrase it. So he asked, as you developed TMS, what clinical application did you have in mind? Was it depression or something else? And I think we did cover it a bit. You were more into the movement motor control, and then Mark George came along. But can you maybe talk a bit about that impact that Mark had, and potentially also then the work that Alvaro did on making the depression story become real? How did that take shape?
Yes. Well, that was certainly the earliest story in the therapeutic area, and of course, the way that it started, I guess people may not remember the full details of this. The way that it started was, as you do in many studies with a new therapeutic, you look at normal subjects. So the first studies that we did, or should I say Mark did, were looking at left dorsolateral prefrontal cortex stimulation in normal subjects to see if they might be happier.
Okay.
that's a hard thing to do, but
Yes.
it seemed like there was some signal there. Then moved into depression, and the first studies, of course, were just single shots. And as we know now, you really need a large number of stimulations before you can actually get a good benefit. But again, with the single shots, there appeared to be, well, there may be something happening. It looks like it's still going to be promising. And that then led to more and more studies where as we got bolder, I guess, we did it longer and more intense and more frequently. And in the beginning, it was a lot of confusion, of course, because there's so many parameters. Where do you stimulate? How much? How long is the train? All those issues would come up, and it took many years to really fully mature the technique. And once it got started, a number of people got onto the bandwagon to also continue to do that work and to be able to learn more and more about what could be a really good benefit. And I suppose I should note that one of the other early things that I got involved with was with Ruby Zangen, Abraham Zangen. He was a fellow in NIDA, and he had an idea along with his colleagues from Israel in terms of developing a different coil system that would potentially go deeper. And his scientific director introduced Bhumi to me, and with the question of whether we could help him develop this coil system, which we did, and we showed that potentially that we showed actually that the field strength fell off more slowly than the coils that we had otherwise been using. And that technology was eventually purchased by Brainsway.
Yeah.
Although that was several years down the line from that development, but that coil was developed from the very beginning as a therapeutic coil.
Got it. Okay.
And so the idea from the very beginning with that was, can we do better in therapy? And so the notion of using TMS for therapy began to be more important, and I suppose that really illustrates that. I suppose that I should indicate that I do have a conflict of interest in that regard, because I got involved with Zangen with that. NIH holds the patent for this coil, which was eventually called the H coil, and NIH shares the patent licensing fee with the inventors, so we get a small portion of that. So, but I've in my studies and publications and everything, I point out that conflict of interest. So it's particularly important to mention it here when we're talking about this topic. But of course, it was something that we got very much involved with because of our basic understanding and group's interest in the way that different coil shapes stimulate the brain and how you actually investigate.
Yeah. It's very interesting to hear, and I, did not think about it before, that you said single shots was the beginning, and it makes sense. Obviously, new technology, you stimulate just once, but from modern views, that seems like a ludicrous small amount of dosage, and then ever since then it has become ever more condensed, and I would say that the culmination of this is probably the SAINT protocol by Nolan Williams, who I also had on the podcast. That is really trying to condense a lot of treatment in a single day and then single week. What do you think of that? Also, maybe because you mentioned before that Jordan Grafman's trial with safety. Is any of that of concern now? Putting so many pulses in, or what do you think about this development of dosage increase?
Yeah, well, I think when you're dealing with dosage, you do have to go slow in the beginning and gradually ramp up. And I suppose the story is relevant also in relation to levodopa and Parkinson's.
Yeah,
levodopa failed for years in clinical trials because the dosage wasn't adequate.
Yeah.
And the first study that demonstrated its use was not because it was a novel therapy, but because more of it was given.
Got it. Yeah.
At that time, so this is a a common situation, but it's the way that you have to do it, and you start low and slow, and you gradually build up and see what's safe, and you work your way up. People in the pharmacology business talk about that as the maximum tolerated dose. You just sort of work your way up, and you see what you can tolerate and what sort of benefit you can get in this type of situation. But at the beginning, you can't start out with a massive amount of stimulation. You have to start out. I mean, it wasn't with a single pulse; it was a single train of RTMS.
Okay.
But,
that makes okay.
Yeah, but
that makes sense.
Right. I mean, we wouldn't have gotten very far with just a single pulse.
Okay. Thanks for clarifying that. Yeah.
So it was a single train, but even that is pretty small, in terms of therapeutic events.
Absolutely. Yeah. So thank you for setting that into relation. So I have another final guest question for the TMS part or the neuromod part, and it's another mentee of yours that you mentioned before, Robert Chen, who's now in Toronto, also very influential. And I think from the question, you already know where he wants to direct the talk to. And he asks about the future of the field. His question is, what do you see as the most promising novel non-invasive brain stimulation technique?
Yes. Well, Robert has gone on now to be very cleverly using low-intensity ultrasound. And I think that is a very nice advance. And I think that it has both diagnostic and therapeutic implications, just like TMS has had. It has the advantage of being able to go deep, stimulation in depth, without stimulation more on the surface, which is one of the problems that TMS has, that you always have to stimulate more on the surface than you can in depth. I must say that, again, in the early days, we tried to convince the physicists that we could do that. And the physicists kept coming back to us and saying, look, you cannot get around the rules of physics. So we had to settle for it. I mean, we didn't in the beginning. We didn't believe physics, I guess, in the beginning, but we really should have. In any event, I think that that is a technique which I think is a good one. I think what will probably catch on more, though, is at least for now, as something, and it's already doing it, is transcranial electrical stimulation of various kinds, either DC or TACs. I think that that is so easy to use, so safe, so cheap, and efficacy has been demonstrating for it that it has the possibility of much more widespread use than transcranial ultrasound, which can be used in the clinic, but how much is going to be used yet, I don't know. But it certainly has promise. But the transcranial electrical stuff which is interesting given that stories I was telling in the beginning about how the high-intensity electric was one of the early things that began this whole field again. I think that has a lot of promise. In terms of, yes, there are many other techniques that are being employed, which I think are interesting. The interfering electric fields is of some interest. Static magnets have some interest. There's a whole variety of things that are potentially out there, but I think in terms of getting into common use, I would think it would be the low-intensity electrical stimulation, which is cheap and easy and very safe.
Yeah.
That's probably going to be used more and more in terms of therapeutic applications.
Sounds great. So moving to movement disorders finally, I'm sorry that I take so much of your time, but in 1964, the famous pianist Leon Fleisher lost the use of his right hand due to musician's dystonia. And based on Wikipedia, you pioneered experimental Botox injections to treat his dystonia. At the time, was this a normal thing to do? And if not, how did you come up with the idea of Botox injections, and how did you come to meet Fleischer?
Right. So as I say, I like to do things, and I got interested in botulinum toxin as a therapy for dystonia. Following the pioneering observations of Alan Scott. Alan Scott was the one who first thought that you could use botulinum toxin therapeutically, and he was studying strabismus, and then he studied blepharospasm, and then a number of other investigators got involved with looking at blepharospasm and looking at cervical dystonia, and my studies have largely been in the hand because the hand is a good thing to look at for motor control. So we were seeing some patients with focal hand dystonia. So I wondered whether that would be a good treatment. One of my colleagues at that time was Fred Hochberg, who was at the Mass General. He was running a music clinic and had seen a lot of patients with focal hand dystonia. We were seeing some at NIH. I ran into Fred. I won't go into the details of where I ran into him. We had known each other for residency days. And I said that I was interested in the possibility of using botulinum toxin. He said he was interested. So we started a protocol at NIH for that purpose, and started seeing those patients and published, I'm not sure it was the first series of patients with focal hand dystonia. It wasn't the first patient. I think one or two patients had been published earlier, but we published the first series of patients using botulinum toxin for focal hand dystonia. So in the beginning, we got a flood of referrals from all over the United States, but as usual at NIH, there's a propensity for the local people to refer more of them. Leon Fleischer was a professor of piano at Peabody School in Baltimore, and he knew Dan Drachman, who was a neurologist at Johns Hopkins, and they knew each other through music circles. Dan had the interaction with the music as well, and he knew Fleischer, and so Dan referred Fleischer to us. Now, at the time, Fleischer's dystonia was extremely bad, and his hand was severely flexed, almost in a fist, and he couldn't get his fingers out, and he couldn't even wash his hand very well. So
and he still gave concerts with the left hand only. Is that true? I heard that.
He was still doing concerts with the left hand. Correct. Yep. At that time. But his right hand was problematic. I mean, he couldn't even wash it. So I got a call from Dan saying, would we accept him as a patient? that first goal would be to release the muscle spasm enough that he could open the hand, because that was really the only goal. It wasn't the goal to get him to play, it was to get him to open the hand. And I said, sure, we would be happy to see him at NIH. So we saw him at NIH. He came down, and we gave him some toxin. It worked very well for him. It opened his hand wide, and he was able to manipulate his fingers. And we went through several cycles, and he said at one point, gee, my hand is open now, and I even played the piano a little bit.
Great.
With my right hand. And it's really a long story, but he then lost interest in botulinum toxin for a few years, tried some other therapies, but he eventually came back to botulinum toxin. Eventually that, together with practice, and perhaps some other things, got him well enough that he could play with his right hand. And then he began performing with both hands. Then he became a poster boy for botulinum toxin and a poster boy for the identification of dystonia in general, and supported the Dystonia Medical Research Foundation, played concerts at a movement disorder meeting, came to NIH and gave a grateful concert.
Wow.
So I think he was a great success for botulinum toxin, but the idea had come from Dan Drachman. Now, interestingly, Dan Drachman, these stories are always very interesting. Dan didn't come to botulinum toxin in a naive way. Dan was interested in the neuromuscular junction. He had done a lot of work in myasthenia gravis, particularly. He was well known in that regard, and he had known about botulinum toxin as a blocker of the acetylcholine release at the neuromuscular junction. So he had suggested to Vernon Brooks, a physiologist in Canada, that Brooks might want to study this too. And Brooks studied that as a way of interfering with neuromuscular induction. And Alan Scott learned about it from Vernon Brooks, basically. So actually, Dan was very important in the chain of being able to identify toxin in the first place as being a potential therapeutic, and through Vernon Brooks, it eventually got on Alan Scott's radar, and he then developed it. So Dan not only referred us Leon Fleisher, but he was a very important person actually in the history of the development of therapy.
Fantastic. Yeah, what a story. So dystonia, so Leon Fleischer had dystonia, musicians dystonia. Dystonia in itself, is a very enigmatic disorder, I think, pathophysiologically, and has remained so. I think. Christos Ganos has two guest questions. One is about that, and I'm going to play that for you as well.
Yeah.
Hello, Mark. It's so great that you and Andy meet together for this episode of Stimulating Brains, and thank you for sharing with all of us your pearls of wisdom, and these are many. So thank you for this, and this is Christos from Toronto. So I have two questions that I would really value your input on, and if you could provide your insights over the vast experience you have through all the years that you have contributed and monitored research across the globe. So the first one is related to the role of cortical neurophysiology in dystonias, and how you believe it has really aided us in understanding the pathophysiology, thinking also from cortical inhibitory protocols, Siddiqi, leaky, etc., to surround inhibition that you have worked a lot, and also then behavioral and cortical neurophysiological studies, thinking of the many studies for a period of temporal discrimination thresholds, etc. So I wonder if you could give us your wisdom, share with us your wisdom on this topic, whether you believe some protocols have really enhanced our understanding, whether they are robust enough, and whether they really help us gain insights into the different dystonic phenotypes, including lumping and splitting. I know it's a big question.
Yes, it is a big question. In order to answer it, it would take maybe 2 or 3 hours to get all the nuances in, because I've lectured on different aspects of that over the years. And let me just try to give some short answers on this so we don't go completely over time. So I think one of the issues, and again goes back to my fundamental concern about normal motor control and pathological motor control. One of the things that I was always interested in was the ability to move individual fingers. And this is a problem for patients that have dystonia. They have difficulty with isolated finger movements, and they have this process of overflow that goes into the other fingers, so it's difficult for them to be able to make isolated finger movements. So this became one of the major interests in our group, trying to understand what is the normal ability, or how can people make individuated finger movements, and then what goes wrong in dystonia. And we approached that using techniques largely of clinical neurophysiology, using TMS over many years. And we explored the cortical processes that are relevant to the production of individuated finger movements, and how that might be problematic in patients who have dystonia. This led us to the idea that there is a process of surround inhibition in the motor system that allows us to make individuated finger movements. This idea had been pushed by a number of people in the past. It actually perhaps started with Denny Brown with the first ideas of it. John Mink did some important theoretical work in that area. But we thought that this was a very important process and began to investigate it as a cortical function. I'll just take one step back and to note that when I was in medical school, I spent a summer working with Hugel and Wiesel, who got the Nobel Prize for part of their work in surround inhibition in sensory systems.
Yes.
So I was primed, okay? I was a primed person for trying to say that, look, you have surround inhibition in the sensory system, the motor system should have surround inhibition too, and we could see it with transcranial magnetic stimulation studies, and we investigated it in all sorts of different ways. I must say that the neurophysiology community and the dystonia community, well, and we also showed that this fell apart in dystonia. So it was exactly what we had suspected. We had a hard time convincing people that any of this was true. we had all sorts of arguments. I must say that I guess I was guided by belief to a certain extent for a long period of time that the nervous system has common principles in surround inhibition. Yeah. And I just couldn't be shaken from that role, and I think that people have now largely accepted it. But much of the data that we had related to studies, physiological studies, using TMS in all its variations, looking particularly at inhibitory mechanisms, because there was the failure of this inhibitory, because there was the failure of inhibitory mechanisms that we could see in patients who had dystonia. So I think that was one of the sort of driving factors there. We then subsequently became interested in another phenomenon in dystonia, which is the task specificity, and tried to understand where task specificity comes from. And we did some studies that were based with MRI that actually showed that task specificity was also a cortical phenomenon that was related to the connections between parietal and prefrontal areas. And then we began to explore that further using TMS methods. So I think that we spent a lot of time studying all these things. And I think that, to go back to Christos's question, there is variability in a lot of these measurements. And I think that that has the nature of the variability has not been understood completely, but it has made it very difficult to get hard, statistically significant results. And that it also means that it is, at least so far, difficult to use any of these techniques on a single patient basis. It would be nice to be able to do that on a single patient basis, because then you could use it diagnostically.
Sure.
But I think at the moment, because of the noise and the variability, we can do this only groups. By the way, there was a recent large meeting just on the variability of TMS measurements that we had. I think that's published now. But it shows all the huge variety of factors that come into the variability and make studies difficult in that regard.
Yeah.
But I think that if you do enough subjects and on all these things, one can understand that these processes are present, and these processes are important not only for understanding the way that the brain works to make the ability for isolated movements, but how the brain works in order to deal with individual tasks, and how that falls apart in patients that have dystonia. Now, much of that is cortical, but I think it's supported by basal ganglia circuits. So the basal ganglia aren't completely irrelevant in this regard, but they don't have the same subtlety that the cortical circuits have. At least that would be the way that I would do that.
Makes sense. Thank you. Starting in 2016 and through to 2021, several hundred US intelligence and military officials and their families reported having symptoms in overseas locations, including China, India, Europe, Hanoi, as well as in Washington, D.C., USA. This became known as the Havanna syndrome, and you were, I think, according to Wikipedia again, among the physicians asked to examine the diplomats. Can you tell a bit about that story? And for me, this is a DJ question into the functional neurological disorders.
Yes, so the Havanna syndrome is a very interesting disorder, and one that is highly political in many ways.
Yeah.
And because of its political nature, those of us at NIH are constrained in how much we can actually talk about it.
Of course.
So I can describe what we have published, but I can't go too much further, I'm afraid, in terms of the details, because of the sensitive nature of the disorder and the highly political aspect.
Of course, yeah.
So, yes, I have been involved in that study. I have seen many of the patients, and all of the results that we've had from that patient investigation are published very recently in the Journal of the American Medical Association. And we did make the diagnosis, as you have already intimated, of a functional neurological disorder in about a quarter of those patients.
Okay.
And the actual specific functional neurological disorder that was common in that group was a disorder called persistent perceptual postural dizziness, or 3P, or PPPD, or 3PD. So that was what we have identified in those cases, and one can read more details, I suppose, about it in that article, and more information will be coming out about this whole story in the long run, but I can't go into too much more detail at the moment, just because of the nature of this particular topic.
Yeah. I assumed as much, but I had to ask because I read about it, so I had to bring it up. I have another. I have another second final guest question by Christos Ganos. His second question that goes into the F&D territory, so I'll play that now.
The second question relates to, and I know this is one of your main interests as well, functional movement disorders within the umbrella of functional neurological disorders. And this question addresses your views on how much evidence we have actually on active inference and predictive processing, and which are used as the main frameworks to explain functional neurological symptoms now. And of course, they are so overarching and all-encompassing that they are in many ways fail-safe. But how much evidence do we actually have for that? And what do you think are the ways forward there? Thank you, and I'm very happy always to hear you, and thank you for everything you're doing.
Well, yes, thank you, Christos, for that question. So I think that question is sort of based on the notion that the brain works in a way of predictive processing in a Bayesian sense, that the brain develops hypotheses about the way that the world works and is constantly checking on the sort of correctness of that view. So that notion works very well with and pretty obviously with perceptions, that when you see something, your preconceived notion about the nature of objects has a strong influence on how you actually see it. And if you find out that you're incorrect in that regard, you can modify your pre-existing belief to be able to recognize that more easily in the future. So your pre-existing notion of the nature of the world needs to be modified as you learn more about the world. Basically, that's on the perceptual side. Now, if there's a mismatch between the way that you see the world and the way the world turns out to be, there's actually a second thing that can potentially, or at least theoretically, occur. And that's what you asked about, active inference. And active inference is that as opposed to changing your belief, you can actively change the world.
Yeah.
So you can, in theory, drive a motor event that will change the world, that will then bring your preconceived notions and the results of the world into congruence. So you can change the world in one of two ways. You can change your belief, or you can have active inference that will change the world for you.
Yeah. Yeah.
Now, the notion of functional movement disorders in this scheme arise from active inference. Where I have always thought that I could understand the process of changing belief, I have never understood completely, honestly, how we could instantiate active inference in brain mechanisms.
Okay.
Now, the person that has pushed the idea of this in the beginning is Mark Edwards, and Mark and I have discussed this many times, and I have asked him that same question that you're just asking me now many times at meetings, and we have, there is no clear answer that Mark has for this, and there's no clear answer that I have either. But let me tell you what I use as a possible rationale, and it goes to your favorite neurological disorder, Tourette syndrome. So a number of years ago, we did studies in Tourette syndrome trying to see what in the brain drove tics. And we found that there is activation in the anterior insula and the anterior cingulate that occur just before tic. And we know that those areas also become active with urge. So, and urge precedes tic, and so when people develop urges, those areas develop, and those areas precede tic, which is a motor action.
Yeah.
Now, it turns out that if you try to identify where belief is in the nervous system, and I've read many papers trying to understand even this, which is true. One of the areas that keeps coming up in relation to belief is, in fact, the anterior insula.
Okay.
So if belief is, in fact, at least partially instantiated in the brain in the anterior insula, we know that the anterior insula can at least precede tics. Now, tics aren't the same as functional movements. They are clearly different. But nevertheless, it shows how the anterior insula can potentially drive movement. And I think that this is as close as that I've been able to get to how you might have a function like active inference. But I would say that I actually don't have a clear answer to that question, and I would think that that's something that really needs to be studied at the moment, and techniques like we could have with functional imaging and brain stimulation can well be tools that we can use that will illuminate this in the long run. We will figure it out. It has to have, if it's occurring, it has to have a physiology that we can study, and hopefully we can figure it out what it is. But since I'm retired, I can't do those experiments anymore. Christos, you have to do it now.
I love it. I'm just realizing we should have probably briefly defined what a functional neurological disorder is in the first place. And can you maybe also comment on, do you think there are some that we currently diagnose as functional that we will potentially in the future diagnose more somatic or otherwise?
So functional neurological disorders are involuntary disorders that can mimic any neurological symptom. And I believe that my own view of it is that they arise, as I mentioned earlier on in our discussion, because of hyperactivity of the limbic system that somehow drives abnormal belief, active inference, depending upon the nature of the situation, into developing these movements, which turn out to be, which appear to superimpose themselves on a nervous system which is actually capable of normal function. So there's nothing, so that individuals with functional neurological disorder are able to function normally, even if they don't. And the don't comes from this abnormality of the limbic system and perhaps a subsequent development of that moment. So I think that's sort of it. I have a much longer definition that I won't,
Of course.
I won't sort of trouble you with at the moment, but that's the sort of idea in it. There was a second part to that question.
So do you think we will relabel some disorders that we currently call functional if we understand them better?
Yeah, so I think that the work that we've done in recent years shows that there are abnormalities in the brain in these patients. Even though their brains are capable of normal function, as I said earlier, they're not completely normal. There is hyperactivity of the limbic system. You can find structural abnormalities in size of the amygdala, in nature of white matter tracts, such as the uncinate fasciculus. So there are abnormalities that are present there, and I think that I don't really see a fundamental difference in a way between functional disorders and other disorders.
Makes sense.
There is brain pathology and brain mechanisms in all of them, and we will probably refine our understanding of all of them going forward. Every year we learn more about every individual disorder. They're all brain diseases, and I think we have to think of them in a family that way.
Love it. Two more very quick questions to wrap up. I want to be mindful of your time. These are more general, rapid-fire questions, so you can answer very briefly if you want to. Any advice for young researchers entering neuroscience or academia?
Right. So the answer to that question that I always give is to find something that you enjoy doing. You should have fun with what you're doing. You should like what you're doing, and then you will like to do it more, and you will have a greater chance of success. If you don't like what you're doing, it's not a good idea.
Love it.
You should try something else.
Sounds good. And then maybe as a field in neuroscience, are there any missed opportunities? So things that you think we should be doing but are not doing well enough?
You mean in the field of what?
As this academic field of neuroscience, things we should investigate or differently or do differently.
Yeah, well, I think there's a lot of progress to be made in many different aspects of neurology, of movement disorders, and of different ways of investigating these different interesting phenomena that we have been talking about. I have been interested, as we've been talking about, in functional neurological disorders, and I think that that area has had a lot of low-hanging fruit because no one has been investigating it for 50, 60 years. And so there was a lot of room for new study, and I think there still is right at the moment. But there's more people getting interested, and which is good, and we'll be learning more about that at the moment. The big problem, of course, that has escaped all of us, and I don't know if we'll ever solve it, but it would be good to, is the nature of consciousness. That's the final goal, I think, to understand how the brain works. How does it generate awareness? And I don't think we have even much good idea about it. There will probably need to be, my guess is, new tools, new insights that will get us there. And I think that we're beginning to understand things like, we didn't get into it, but the nature of volition, the nature of voluntary movements, the nature of free will in some ways. but how the brain converts the processing of sensory stimuli into perceptions, how people develop thought, all those things are they're not low-hanging fruit; they're high-hanging fruit.
Yeah.
But
and I mean, there is the book by Dan Dennett that's called Consciousness Explained, who unfortunately just passed. So we could just read that book. It explains it. No, but I totally agree.
Yeah,
still lots
right.
of.
Yeah, right. We haven't gotten there quite yet.
Yeah, sounds good. Okay, any question that I should have asked? So any topic that, I know I asked a lot, but anything you would have loved to talk about more before we stop?
I have hundreds of anecdotes about various things, but I think we have probably covered quite enough.
Okay, great. Yeah, and I mean, I would love to keep talking for hours, but I have to be mindful. We're already over time. Sorry for that. And thank you one more time so much for agreeing to join us here. This was a big honor and very enlightening and very insightful. Thank you.
Happy to do it. Thank you for the opportunity.